Modern forecasting equipment. Page 1. Today, we rely on modern forecasting technology and engineering to predict weather patterns. The modern age of weather forecasting began with the invention of the telegraph in 1837, which allowed forecasts to be made by knowing the actual weather conditions in the distant places. Even more progress was achieved during the 20th century when engineers and scientists designed computers to make numerical weather predictions, computer simulations, of the atmosphere. These simulations take information about the present weather and use the computational tools of physics and fluid dynamics to predict atmospheric states. Basically, the complicated equations used by the computer project project how the working fluids of the atmosphere, that is, wind and water, are expected to change with different atmospheric conditions, that is, temperature, humidity, and pressure. It is important to note that before any fancy computer simulations can be made, raw weather data, actual weather measurements, must be collected. Page 2, Weather balloons. Weather balloons carry instruments high up into the atmosphere. The balloons launched every day all over the world carry a radiosonde high up into the atmosphere. The radiosonde is a small battery-powered device that collects information about atmospheric pressure, humidity, and temperature. These data are then transmitted to a ground antenna via specific radio frequencies. Wind, speed, and direction are calculated by tracking the weather balloon using GPS or radio direction finding. The flight of a weather balloon doesn't last very long. The weather balloon is filled with either helium or hydrogen, which lifts the device into the atmosphere at a rate of 1,000 feet per minute. In its flight, the weather balloon can ascend to over 35 kilometers, or 115,000 feet, and drift more than 300 kilometers, about 180 miles, from where it was launched. As the balloon ascends, the pressure decreases, which causes the balloon to expand from an initial diameter of 1.5 feet to 6 to 8 feet. Eventually, the balloon expands so much that it ruptures. The radiosonde has a parachute attached to it, so that it is less likely to cause damage when it returns to Earth. Most radiosondes are not found after they return to Earth. Of there are approximately 70,000 radiosondes deployed every year, only about 20% are found and returned to the National Weather Service for reconditioning and reuse. Satellite technology, page 3. What about the big picture? Weather satellites are another engineering marvel that enables us to see what the Earth and clouds look like from space and give us a more comprehensive view of Earth's interrelated systems and climate. Figure 4 was created using data from 4 different satellites. The red dots you see are fires burning on land areas, and the large aerosol clouds over the Atlantic Ocean are from the burning of biomass in Africa. You can also see dust and clouds wrapped around the planet. Page 4. Weather radars. What if you wanted to see inside a large cloud or storm to analyze its structure and gauge its potential to cause severe weather? Is it possible? Military radar operators asked the same question during World War II when they noticed noise in returned radar echoes due to weather elements such as rain, snow, and sleet. When the war was over, many of these military radar operators became engineers to develop a use for the noisy echoes. Now, we have a weather radar, a special type of radar that uses radio waves to see how precipitation is behaving in a cloud and how it might change. Radar stands for radio detection and ranging. Basically, a radar is an electronic instrument used to determine the direction and distance of objects that reflect radio energy back to the radar site. Weather radars use radio waves to locate precipitation or rain and determine its type: rain, snow, sleet, or hail. These also calculate the motion of precipitation and forecast its future position and intensity. All weather radar works by the process of scattering, in which radiation energy is reflected by small particles, as shown in Figure 5. So when weather radar sends a radar beam out into space, the precipitation particles in the atmosphere cause the radiation energy to scatter. The motion and behavior of the scattered radiation is read by the radar site and translated into important weather information. Page 5. The Doppler radar. Most weather radars are Doppler radars, which can also detect the motion of radar droplets. Doppler radar gets its name from the Doppler effect. Have you ever listened to an ambulance siren or a train whistle as it was coming towards you? You probably noticed that the pitch of the whistle changed as the train passed you and moved away. This change in the frequency of sound is called the Doppler effect. A Doppler radar measures the changes in the frequency of the signal it receives to detect the intensity of precipitation, estimate wind direction and speed, and predict hail size and rainfall amounts. Doppler radar gives forecasters the capability of providing early detection of severe thunderstorms that may bring strong damaging winds, large hail, heavy rain, and possibly tornadoes. Figure 7 shows the radar reflexivity image of the Oklahoma City Twin Lakes Doppler radar taken on May 8, 2003, just before a tornado hit the General Motors plant in the area. Because the Doppler radar shown is the early formation of the tornado provided by the NOAA, National Weather Service, with 30 minutes advance warning, officials were able to move 1,200 employees to a shelter before the tornado hit.